Hello, and welcome to another edition of SETI Live. I am your host, Beth Johnson. With me today are Dr. Marie Cody from the SETI Institute and her intern student from our summer REU program, Marlee Rapp, who is, I believe, from the University of Michigan. Is that correct? All
Yes.
right, fantastic. Just wanted to say hi to everybody who's watching out there on YouTube, Facebook, Twitter, and Twitch. Please let us know where you are watching from and we will give you a shout out. And as a quick reminder, we are a nonprofit and we are supported in our outreach programs by your bits, your subs, your stars, your super chats. All of those things go to keeping this program running. So if you have a moment and you have some spare bits laying around, you know what to do. We are here today to talk about this summer REU program that Marlee is working on with Dr. Cody. They are using NASA's Transiting Exoplanet Survey Satellite, or TESS, to try and develop an algorithm for looking for technosignatures from exoplanets. So I want to welcome both of them to the chat today. And I guess we're going to start off and just sort of say, what's this project entail, Dr. Cody?
Yeah, so the TESS satellite, which is in orbit in space, is looking at tens of millions of relatively bright stars all across the sky. And it takes repeated images, just basically picture after picture of all these stars. And what we do as astronomers is we translate those images into measurements of the star's brightness. So for all of those tens of millions of stars, what we're working on is producing a time series of the star brightness as a function of time. That's a light curve. And that brightness can encode information about each of the stars, what's going on the star, around it. So if you're familiar with variable stars, sometimes, if there's a planet around the star, it eclipses the star and you see a little dip in the brightness. Well, it turns out if there are larger objects, for example, another companion star or something more bizarre like an artificial structure put in by an intelligent civilization to harvest energy, those objects in orbit around the star can also occult it and produce a dip in the brightness, which we would then see in the light curve. So we've never seen anything artificial, but we now have a good chance to sift through data on these tens of millions of stars and see if we can find a signal. It's probably unlikely, but in the end, we can at least say we looked through 50 million stars or so, and we didn't find anything, and here's a limit on that phenomenon, or maybe we will hit gold.
So was this project inspired partly by Boyajian star, the one where everybody thought that, well, not everybody, but there was a growing interest that it might have been an alien megastructure causing the unusual dimming to the star?
Absolutely, yes. So that particular object was found with the previous NASA telescope that was doing similar work looking for exoplanets, among other things, the Kepler mission. And in fact, citizen scientists were largely responsible for noting the interesting behavior of Boyajian star, which was sort of a relatively constant brightness interspersed with these pronounced fading events where the star would suddenly get darker. And it didn't really match up with any astrophysical phenomenon that we knew of at the time. We still haven't quite figured out what's going on with the star, but the short story is we believe there's some kind of dust or small comets that are occulting the star. But initially, it was also proposed that this could be a candidate for these artificial alien megastructures in orbit around another star. So that kind of spawned interest, even though it's not the leading hypothesis. It got people thinking about, if we looked at a much larger data set, so TESS is looking at tens of millions. Kepler in its prime mission looked at about 200,000 stars. So 1 out of 200,000, if you then scale that up to, well, how many might be present around 50 million, you have a much better chance of finding something, whether it's comets, which we're also kind of looking into, or something more bizarre.
So what were you working on before this?
So I'm pretty new to the game of SETI, and I've primarily been interested in the youngest stars. And I got into using these space telescopes because it turns out the youngest stars also have interesting stuff orbiting around them. It's not produced by aliens, but it's the material left over from their formation. Lots of dust and gas. If you've seen these beautiful pictures of nebulae in our neighborhood of our galaxy in space, dust and gas, pretty colors and structure, you might have seen little stars kind of dotted around the area, usually kind of just popping out from the clouds. Those are the youngest stars. They're generally a few million years old, which is considered young in astronomy. So all the material that's kind of swirling around them and potentially forming planets causes crazy variations in the brightness of young stars. So I've been looking at that and trying to figure out how we understand what's going on physically in the neighborhood of young stars, how they form planets early on, and phenomena like that. But it turns out that the brightness dips produced by material around young stars is similar to what we saw around Boyajian's star. And it's also similar to what we might expect from some kind of artificial structure. So the two research areas, even though they're a bit different, studying the young star environment and looking for alien life, the techniques that we use in terms of analyzing the data are very similar, actually.
Okay, well, I want to bring Marlee into this conversation, but first I want to give some shout outs to our viewers. We have people watching from Mexico, India, California, Tennessee, Denmark, Texas, England, New Jersey, Australia, Bangkok, Canada, wow, Tunisia. I mean, it's a global audience today, so that is very, very exciting. Welcome everyone. So Marlee, can you tell us what a technosignature is and how it's different from a biosignature?
Yeah, so technosignatures and biosignatures are both signs of extraterrestrial life, and a technosignature is a sign of technology made by the civilization, while a biosignature is a sign of the biology. And so what's different about them specifically is that with a biosignature, the civilization doesn't need to be intelligent because they can emit gas, they can do whatever, they can live, but they can't make technology. So with a technosignature, the civilization must be intelligent. So they're a little different. And so with technosignatures, a couple of the ways that we look for them is with radio astronomy, looking for radio bursts, or with stuff like this, where we're looking for eclipses that are maybe not so periodic, or uneven or strange depths, uneven depths, inconsistent. While with biosignatures, we might be looking at atmospheres of exoplanets, like what the James Webb Space Telescope will be doing hopefully within the next year. So.
Okay, fantastic. So how are you adapting tools from these studies of young stars to find these technosignatures? What's the plan here?
So when Anne-Marie was working on the Kepler mission, she created the MSTAT metric, which we use to measure the amount of dippage, I guess you could say, like how much it dips or spikes compared to the overall average of the light curve, the long-term trend line. So we can use that metric to look for dipping among a lot of our light curves.
Okay. And what are you working on right now? Like what are you working on specifically in this project?
So right now we're working on getting the MSTAT value for as many light curves as possible, and working on speeding up that process and filtering through and looking at the stars that have higher MSTAT values, which means that there are significant dips.
Yeah, I
And
should say, I was
oh yeah,
just
go
going
ahead.
to add that looking through light curves for tens of millions stars is a time-consuming process, as you can imagine. We have like special places where we store our data because it's a lot even to keep on just a personal computer.
Mhm.
So in the past, you know, you could have people just look through all the data and say, this star has a fading event, this star has a fading event. But when you get up to the tens of millions, you need statistical algorithms. And so that's what this M statistic, which we invented that Marlee's referring to, it basically picks out anything that has fading events from a rather continuous brightness level, and we can do so essentially automatically, but it's taking time to actually get our software to move fast enough that we can return results on these tens of millions of objects.
So you're developing a machine learning algorithm. How are you training it? What are you training it on?
So what we're doing now is, I would say it's actually a little simpler than machine learning. One of our colleagues at SETI, Daniel Giles, is he has many more statistical metrics that he's measured on our data in addition to the one Marlee's working on. And we aren't actually training on anything. There's different versions of machine learning, supervised versus unsupervised. So what we're actually doing is just looking at the aggregate statistics and clustering them. And there's different ways to do that with machine learning. And we're looking for the oddballs that don't fall in clusters. And then we perform a more in-depth analysis. For Marlee's project, in some sense, we have trained at least ourselves on these young stars that I was working on. So the statistic that measures the dips in the light curve, this M value, it has been shown to pick out young stars with fading events very well. So we know that when we get certain values of this M thing above a certain threshold, that we're likely to have a star with the fading events, regardless of whether it's young or not. So yeah, in some sense, the threshold has been set on the young stars. Yeah, and stellar eclipsing systems as well. Those show up.
So if you find something interesting, what's the process?
Well, let's see. Marlee, do you want to talk about sort of the initial stages of how we would vet it, and then I'll talk about more long term?
Yeah, so one of the things that we would look for is whether or not the fading events are periodic or quasi-periodic or totally not periodic, as well as the consistency or lack thereof of the depth of the dips. And we'd also, like Anne-Marie was saying, look at whether it's an oddball or not with that clustering. And if we think it's like a candidate for something funky, whether it's aliens or just a not well-known astrophysical phenomena, we have time at what was the name, Anne-Marie, of the observatory?
Oh, the Las Cumbres Observatory Network.
Yeah, so we could use that observatory to follow up and look at the star of interest and do a deeper dive investigation and try to rule out any hypotheses, including alien civilizations, and
Yeah,
eventually publish.
one thing I should note for the viewers who aren't familiar with TESS is that it's a single broad bandpass. So it's effectively looking at stars in white light. One of the discriminators of dust versus something opaque, like either rock or some giant artificial panel that aliens have built, is that the opaque things create the same depth of the fading event, regardless of what wavelength you look at. Whereas dust tends to be have deeper fading events when you look at red wavelengths versus blue. The analogy I like to use is like when you're looking at the sunset, the sun is going through the atmosphere and the light is passing through all those particles in the atmosphere. and it causes the sun to appear more red in the sunset. It's similar when you're looking through a lot of dust, the light is preferentially reddened. And so the thing is, though, with TESS looking in white light, we don't have that color information that we would like to have. So this ground-based follow-up is specifically to fill in that gap. Now, we won't be looking necessarily simultaneously, so we have no guarantee that the events that we saw in TESS will repeat when we look at them later from the ground. That is kind of the caveat. But we can look at different wavelengths. We can say, okay, if this star repeats some odd behavior, what does it look like in a blue filter versus a red filter? And if we see that the event is deeper in the red versus the blue, that's a good indication that it's some kind of dust structure and not an opaque, object that's passing in front of the star. And Marlee earlier mentioned we have colleagues at SETI Institute and at University of California, Berkeley, who are looking for technosignatures from other angles using radio wavelengths. And they're constantly monitoring to the sky for radio signals that may be artificial in nature. If we find something interesting, we're going to pass our target information along to those colleagues, and they can take a closer look to see if there's any other type of signal coming from the particular stars.
Would you be asking for some telescope time on the ATA itself?
So I'm not quite sure the details, but I believe it would be under whatever existing programs our colleagues already have up and running. So so they would just insert it into their queue, and there's already actually some collaboration between the TESS mission and the SETI Breakthrough Listen program at Berkeley. Exoplanets are found in TESS data as well, and exoplanets that are potentially promising in terms of harboring life, like maybe they're in the so-called habitable zone of their planet host star, so they might have liquid water, the temperature seems suitable. Those targets are already being passed on to the radio programs just to see if there's anything coming from the planets without knowledge of whether there's life on them or not.
So the things that you're looking at, these stars don't necessarily have confirmed exoplanets, correct?
Right.
Okay.
So only of order a few percent of exoplanets can be seen with the TESS satellite, because you have to have the right alignment of the planetary orbit with the Earth's line of sight view. So if you can certainly have planets around stars that just aren't visible to the TESS that perhaps have some signs of technosignatures, but the planet does not happen to orbit exactly in the plane of our line of sight and eclipse the host star. So we don't want to restrict our search to systems where we can detect the planet, because there could well be planets there that just aren't observable, or maybe they're too small, maybe they're Earth-like. Those are hard to find because the depth of their eclipse, their transit depth, is so small. Whereas if they built a huge structure around their central star, that might be more observable than the planet itself.
So that brings me actually to a question from our audience. Are you looking for Dyson spheres? Is that one of the things that's sort of kind of on the list of possibilities?
Yes. That was one of the theories for Boyajian star, was that a Dyson sphere, which is a large structure around a star, was at least like panels of it or sections of it, or whatever kind of form it takes, was transiting in front of the star, but in our line of sight. So that would have caused some irregular dips. So that could be what we're looking for. That's one option.
What are some of the other options that you think are possible here?
So one of them is dust, because when Boyajian star had some follow-up studies, they concluded that it's probably dust. Another is like really large swarms of comets, or If we're staying on the alien track, maybe instead of a Dyson sphere, maybe like a large spacecraft of some sort or some other sort of interesting technology. Or sometimes, well, with Boyajian star, it was also considered things like clouds within our own atmosphere or between our system and that system or within that system, as well as intervening objects such as black holes, which may block some of the light, and lots of also more astrophysical phenomena we might not even know about.
Yeah, I would say if you have a pure a Dyson sphere that's completely enclosing the star, you won't get any signature apart from extra infrared radiation emitted by that object. So we are sensitive to things that are in orbit around the star but have gaps. So we're thinking of like any kind of paneled structure that has both the panel aspects and then holes in between it so that the starlight can come through at times. So we're collaborating with another summer intern who's working through Berkeley, who is using a software code to simulate different kinds of structures with all kinds of shapes and sizes, and produce simulated light curves. And we are actually inserting some of those artificial fake signatures into our data set and then seeing if we recover them. And the good news is we have been able to pick out most of them so far with our machine learning algorithms. So that's a good sign that if there's something strange out there, like a Dyson sphere or similar, then we could pick it up.
Fantastic. I'm just going to give a shout out really quickly, a couple more. It looks like we have people watching from France, some more from Thailand, some more from the United States and New Zealand now. So, wow, that's, again, it just gets bigger and bigger. Fantastic. And once again, as a reminder, we are a nonprofit 501c3. So all of your bits, subs, super chats, stars all go to keeping this outreach program running. So thank you very much for anybody who is thinking of or has contributed in the past. Greatly appreciated. Marlee, I want to ask you, I was in the 2013 cohort for the REU, so I know a lot about the program from that side of it. What's been the most interesting thing research-wise that you've done so far?
So before this, I was working with Dr. John Monnier from the University of Michigan on TESS data as well. And we were looking at, we were identifying and characterizing eclipsing binary star systems where they transit in front of the star and they'll create periodic dips as the stars block each other's light. So it's similar work to what we're doing here. We're working with a lot of the same data and looking for similar fading events. So what I found really interesting was like the different software we're using, the different approaches we're using, how we're storing the data. And I found that it's really useful to, like research with different groups and find out what each group's style is. And I've learned a lot of techniques from each respective project that together has taught me a lot about the TESS mission and looking at light curves and what research is like.
Fantastic. So, and then on a personal front, what's been the most interesting thing that you've experienced so far this summer?
So growing up, one of my favorite movies was Contact, starring Jodie Foster. And the main character of Contact is actually based on Jill Tarter, who helped found the SETI Institute. So we actually got to, during one of our field trips here, we got to Zoom with Jill Tarter and watch Contact together, and she was able to give her commentary and opinions and little side notes on stuff in Contact. And so that was like super interesting, super cool. I was like kind of starstruck. And not only that, but in the SETI Institute, there's a picture of Jodie Foster that is signed by Jodie Foster herself.
I have to say that was definitely one of my favorite moments too. So I completely agree with you. I'm really glad that tradition carries on because it's it's a really good one for everybody involved.
Yeah.
So what's next for you after the summer is over? What's your plan? What's your career trajectory right now?
So far I've only done research with the NASA TESS mission and looking at light curves. So I'm going to be a junior at the University of Michigan. So with my remaining time, I really want to experience other fields within astronomy before I commit to one in grad school. So I am setting up, possibly working with another professor at the University of Michigan, maybe looking at galaxies and how stars movement affects galaxies, or there's a lot of topics he works with, but mainly galaxies, and what topic within galaxies I'll be working on is still a question mark, but I'm hoping to explore some other topics within astronomy before I go to grad school.
Solid plan, solid plan. Before we start to get into audience questions, which if you have questions, please feel free to post them and they will get shared to me. Dr. Cody, what is next for you? What's the plan on this project? Where?
Yeah, so this is actually it's a multi-stage, multi-year project. We're in year one right now, and our goal is just sifting through all the data, identifying all the interesting things. We've still kind of barely gotten going because the data has various shall we say systematic effects that are artificial things, but they're generated by the either the telescope or where it's looking. In particular, there are issues with scattered Earth light. So the light coming from the sun bouncing off the Earth, the telescope is still sufficiently close to Earth that it's affected by that. So we've spent most of the time so far figuring out what is a real signal from a star, whether astrophysical or artificial or et cetera, versus some of these systematics. So our goal for year one is to finish looking through, find all the interesting fading events in these stars. And then in year two, we begin our follow-up of any interesting targets that we've had. And then from there, it depends on if we found anything that's a smoking gun for a technosignature or not. If not, then we're going to work on basically writing up the results and saying this is a limit on the fraction of relatively nearby bright stars that could have very intelligent civilizations that have deployed artificial energy harvesting structures or communication structures. If we do find something, then we will be following it up and basically exhausting all the other explanations before we put it out there that maybe we found something interesting. Don't really want to say, oh, we found aliens, and then have to go back on it and say, oops, we were wrong. That's not good. So we have to be very, very thorough in our search. We are so far, our project is funded to look through the first 2 years of TESS data, but some of your listeners may be aware that TESS is now starting its 4th year of observation, and we have the TESS Science Conference going on this very week, where we're discussing whether TESS might continue for a 5th or a 6th year and beyond. So it might be logical to expand our search and actually extend the project if we want to make our statistics even better. So we'll see what happens with that.
Okay, well, I'm going to keep my fingers crossed that TESS gets extended because I think it's a really valuable mission. Dr. Cody, do you think that, this is a question from the audience, I'm going to start in on these. Do you think that the James Webb Telescope will be used to help look for technosignatures? And what kind of data gathering improvements will it offer?
Yeah, so James Webb Telescope is much used for much more targeted searches. So TESS will look at huge numbers of stars with James Webb Space Telescope. You basically already have to have like one or a few interesting stars. They have to be sufficiently bright. So what astronomers are doing with their exoplanet searches is they're culling down the known exoplanet list to the ones that are most promising for harboring life and the most observable. So they have bright host stars. And it's not too big a list. I mean, it could be like 10 or dozens or something compared to tens of millions. So if we found a promising technosignature through our technique, it might be logical to then we first have to actually see if there's observable planets in transit. And if there are not, then James Webb Space Telescope probably isn't going to help us too much, because you need to see the starlight passing through a planet atmosphere, and that planet has to be transiting across the face of the star. But it's limited in the number of stars that it can follow up. So it's a very complementary telescope, I would say. But probably our first method of follow-up will be to use smaller ground-based telescopes that we have ready access to before we go to the space telescopes, which are harder to acquire time on as well.
There's another interesting question here. We talked a little bit about how you can use this for young stars. Is it possible to use this method to find protoplanets around those young stars?
Possibly. So the trick is, if you want to find young planets, you have to be able to distinguish their transit signals through all the other variability that's happening. So that makes it more challenging. By far, the vast majority of planets that have been found around other stars are in orbit around sort of middle-aged stars, like billions of years old, like the sun. Those are relatively quiet because there's not so much dust and gas swirling around them. So if you can imagine the brightness of a young star that's kind of roller coaster-like and doing crazy chaotic stuff, you need to find a less than 1% dip that's periodic amongst all that. It's hard to do from a statistical standpoint, but there's also a physical reason why it's difficult. The dust and gas is typically in the form of a disk. The protoplanetary disk is kind of a pancaked shaped structure around the central star that's in orbit around it. If you have a planet forming, it's also in that disk. So if you want to see a transiting planet, it has to be going in our line of sight, but so is all that other material. So you'd probably only see a transiting planet if it's somehow been kicked out of the plane of the disk, or if you have some other way of detecting it and the disk is face on and you actually take an image and see it. So at other wavelengths like sub-millimeter observatories, millimeter observatories, astronomers are actually trying to take pictures of these protoplanetary disks and see if there are gaps cleared out by planets. Very challenging just because of all the stuff left over from the formation that's there.
So I'm going to take one last question from the audience because we have reached our half an hour, and I don't want to keep you guys too long this morning. Do you think more data can be generated in the future that can compare the same patches of sky?
So does that mean to revisit? Yeah. Well, TESS is actually doing that right now. So the mode of observation so far is that each star is observed for about a month long. But now that the TESS is in its extended mission, some of those stars are being revisited. So you can get a month-long observation time series, and then like a year later, TESS might come back and do it again. That's already happened for a lot of these stars. So we do have that with the telescope. But I should say there are a number of ground-based wide field telescopes surveys that are in operation now that contain some historical data on primarily the very bright stars. And so we are kind of coordinating a bit with those surveys so that if we see something with TESS, we can say, go back to another survey that might have a decade worth of data and say, did they see something interesting? The caveat, of course, from the ground-based telescopes is they don't have a continuous data stream. They've got weather that comes in, daytime, et cetera. So their time series are much more sparse. It's harder to visualize, was there a dip there or did we miss it? But there's certainly data from other telescopes, and we can follow up when if and when we find something of merit.
Fantastic. This is a really fascinating research project to me. Like, I think this is just really a great way to use the TESS data. So I'm to see where this goes. I think we've kind of reached the end of our time. So I just want to say thank you to Dr. Cody and to Marlee for joining us today. This was wonderful. Thank you so much for answering all these questions. Was there anything I didn't ask that you wish I had asked?
Not that I can think of.
Okay, great. All right. So if you two can stay on after we go off air, that would be fantastic. I'm going to wrap it up now. Thank you everybody for watching, for tuning in today. We all really appreciate that you have come to learn about this science. We will be back tomorrow at 2 p.m. Pacific with another SETI Live with our Frontier Development Lab. They're going to talk about lightning. So that's going to be really interesting. Join us again tomorrow, and make sure that you do the things like subscribe, all of those things so that you get the notifications when we do go live. Follow us on social media. And if you want to learn more about the SETI Institute or you want to make a donation through our website, please go to seti.org and follow all of the various links. You can also subscribe to our newsletter and get our updates there. So once again, thank you, everybody. Thank you, Dr. Cody. Thank you, Marlee. Good luck on your project and good luck with your undergrad work. Very excited for you. And we'll see you guys next time.